Design of a helical spring. There are basically two types of equations which are necessary for the design of a helical spring. The first one being the load equation and the second one deflection equation. Now if we consider a simple helical spring, a compressive force P acting on it, then the forces which will be acting inside the cross-sectional area of the spring are of two types. Firstly, there will be a simple tensile force, and another thing that will be acting will be the torsional shear stress. As you can see over here, the force P is at an eccentricity of radius r, and this what ends up forming a torque at the ends of the spring, and this torque results in the shear stress formation. So the net stresses that are acting inside the cross-sectional area of the spring can be given by the equation tensile stress plus the shear stress. Now the tensile stress is nothing but force upon area, which is equal to stress is nothing but force upon area, which equals the force P divided by pi by 4 d square, where d is the cross-sectional area of the spring, is equals to 4p by pi d square. Now let's find out the torsional shear stress which is acting inside the material. Now we all know that the torque is nothing but force times the eccentricity or the radius, which over here is P times r and radius is P times diameter by 2. So this equals to Pd by 2, and the shear stress which I was talking about is equal to 16 mt by pi d cube. So when we substitute mt over here, what we wind up getting is pi d cube times Pd by 2. This thing gets cancelled out, so 8Pd by pi d cube. So the net shear stress that will be acting inside the cross-sectional area is equal to 8Pd by pi d cube and this thing, the tensile stress, plus 4p by pi d square. Now to make the whole equation look like the one which you currently see in your textbooks, you can convert it into something like this: 8pd times pi d cube. To make this equation look more like the one which you see currently in your textbook, I can multiply it by 2 up and below, and also small d and the capital D. So what this winds up giving us is equals to 8pd by pi d cube plus. Now as you can see, we are going to take out the common things from this part of the equation, or the things which are going to take out common are exactly these terms. So what we wind up getting is 8p capital D by pi d cube, bracket 1 plus, so 8pd got out. Only thing that left is the small d. Pi d cube also got out, so 2 times capital D. Now this term over here 1 plus d by 2d is nothing but the shear stress concentration factor. Basically, this term gets replaced by another term, which is denoted by the letter Ks. So what we wind up getting as the final equation is, now over here Ks is the concentration factor which only takes into consideration the tensile stress and the torsional shear stress. There is another reason for the generation of stresses inside this cross-sectional area of the spring. That is due to the curvature of the spring, and to account for this we have another factor which is known as the Wahl's factor, which is developed by A dot M dot Wahl, which is derived as 4c minus 1, which is derived as 4c minus 1 by 4c minus 4 plus 0.615 divided by, now c over here is just a ratio. C is the ratio of capital D by small d. So the stress concentration factor, the Ks term, can also be written as 1 plus 1 by 2 times C, because C is nothing but D times capital D times small d. Now, since I have already derived the equation for the stresses that act inside the cross-sectional area of the spring, let's derive the equation for the deflection inside the spring. Since you all know by the torsion equation, that is T by J is equal to tau by R is equal to G theta by L, this thing can be rewritten as theta equals to mt over the T can be also written as mt times L divided by J times G. Most of the terms on this equation can be replaced by something else. Now, since I had already defined what mt is nothing but P times T by 2. The length is the total length of the spring, the entire length of the spring that is required to form the coils inside the spring. As I had just drawn a simple helical spring, as you can notice over here, the spring is a combination of number of turns of the rod, and the number of turns can be represented by small n, and the diameter of the entire spring can be represented by capital D. Circumference of a circle is given by pi times d. We can say that the entire length of the spring is nothing but the number of times pi times d occurs, or the number of times these rings occur, or the total number of springs times the circumference of a single. We can say that the number of rings, number of individual rings which form the spring times the circumference, and the circumference of the spring can give us the entire length of the rod which will be required to form the spring. Hence, as I just said, we can rewrite this as n pi d, that is the length of the spring, and the J over here is the polar moment of inertia of the rod, of the bar that will be required to form the spring. This is a standard formula which I will just going to copy and paste. And G is the modulus of rigidity, we will not be changing that. So when we solve this equation, what we wind up getting is 16pd square times n divided by Gd raised to 4. Now what this gives us is the angular displacement of the spring, of not the entire spring but as I just drawn earlier, and we take into consideration the force P that is acting. This is the force P, and the spring comes over here and experiences the deflection over here. Now this angle is 2 times theta, and the only one side of it, and the angle that is formed only on a single side is equal to theta. Now since I want the deflection which will be faced by the entire spring, I can convert this theta into the linear displacement of the spring. Since the linear displacement can be simply approximated inside this single joint, is equal to theta times length of the theta times the radius, that is this thing, is equals to r. It can also be written as theta times d by 2. What this thing says is the deflection that will be faced, this length, is equal to the angular displacement times the distance from the center of rotation. Therefore, theta can be rewritten as 2 times deflection divided by t. Now when we replace this formula in the above equation, what we wind up getting is 2 times deflection by d equals to 16 d square m by g d raised to 4. Now all you have to do is this thing, and for the linear deflection of the spring is given by the formula 8pd cube n by g d raised to 4. Now in this entire equation, when we consider spring, the force that is acting on it, that is P, is directly proportional to the deflection that it is acting on it, and the constant of proportionality which makes this thing true is given by the letter K. It is also known as the rate of the spring, and it makes the equation true. So I can substitute this K in this equation for the rate of the spring. So therefore deflection is equal to the force P upon the rate of the spring. So the final equation is going to be equal to P times K equal to 8pd cube by n by g d raised to 4. So the P cancels out, and therefore the rate of the spring is given by g d raised to 4 by 8d cube by n. Yeah, that's it. So these are the important equations which are required for the design of a helical spring. This is the first one. This is reflection of the spring, and the most important one, that is the stresses that get developed inside the material in the spring. Yeah, remember these 3 formulas to design a helical spring. Thank you.